Inflection points. An inflection point is where the graph changes concavity. So we have concave down to concave up. This point right there is called an inflection point. So we say that a curve is concave up whenever its shape is like this. Well, I'm going to put, oh, there we go, happy face. Things are looking up, you're smiling, you're happy, you're in calculus, concave up. Okay? The graph is said to be concave down. You're feeling down, you're sad, you're in English class, you know. Concave down. So what it means in this statement, it says if all of the tangents, if the curve lies above its tangents. So if I start drawing tangent lines on this one, can you see the curve is above the tangent line? If I draw one here, the curve is above the tangent line. But if I draw tangents on this one, the curve always is below the tangent lines. So here we want to look at where this function is concave up and where it's concave down. So I'm going to do concave up in purple, and I'm going to label concave down in red. So we can just sort of color code this along the way. So I'll start with my purple. Can you see that this section of the graph is all concave up until point P? And then it's concave up from Q up to there, and from there up to there. And it's concave down in this section and this section. Ooh, I maybe shouldn't have chosen purple and red. Can you tell the difference between those colors when looking? Are they distinct enough? Good. I guess I could have picked worse. I could have picked red and then just a little bit not as red. That would have been worse. Ooh, here's your word of the day. I believe that point is called a cusp. At points P, Q, and R, the graph changes concavity. So we look back at the points here, changes from purple to red at P, from red to purple at Q, and then from purple to red again at R. Those places where it changes concavity, that's called your inflection points. So to help us graph things even better, we're going to graph maximum and minimum points, and we're also going to find these points where it changes concavity. And we can do that with the second derivative. So if the first derivative is the rate of change of the function, the second derivative is the rate of change of the first derivative. So in these cases, in both of these cases where we have things concave up, if we look at the tangents on something that's concave up, our tangent goes from 0.24, 1.07, 4.05. If we look at the tangents here, they go from negative 1.4, here it's 0, to 1.6. If we go from left to right, let's word this different. If we go from left to right, the values of the tangents are increasing. And so if we found from our first derivative that when we plug things into our first derivative, it would show our function is increasing if the first derivative is positive and decreasing if our first derivative was negative. Now, if we go to our second derivative, if we find our second derivative is positive, that means the tangents are increasing. And if the tangents are increasing, we'll have that things are concave up. So what's going to happen is we're going to do something very similar to what we did with our first derivative and our sine diagram to find out concavity. So here, going from left to right, the values of the tangents are increasing. Wow, I'm just going to ask you, do you think that says increasing? Is that close? I was running out of room. The computer has something built into it. We're going to do this later. Okay? It says, I think I can read your writing. So I click on it, and the best it can come up with is, man, my writing is bad. Is that close to increasing? No. Sorry. So going from left to right, the values of the tangents are, well, now I can't even erase that. Here we go. So beautiful. Look at such nice penmanship. Increasing. It's like even like a happy face down the perfect. And if we look at tangents where the original graph was concave down, if we go from left to right, the tangents are decreasing. And if your tangents are decreasing, then your second derivative would have to be negative. Because whenever things are negative, it tells you that one function up is decreasing. And if you go two functions up, that would mean that it's concave down. So here's our test for concavity. If our second derivative is bigger than 0, then we can say that the function is concave up over that interval. And if the second derivative is less than 0, we can say that it's concave down. So what we use to remember this is in the second derivative, if you get positives, I actually like just making positive cyclops smiley faces. Okay? If it's positive, it's concave up. If it's negative, it's concave down. Right? Happy, sad. Easy to remember. And any time that you change from positive to negative, and your second derivative is equal to 0 at that point, we have a point of inflection. So, to show that we have a point of inflection, we need to show two things. We have to show, number one, I know it says it here, but I'll write it again. You have to show that it's equal to 0. Maybe I'll choose a different letter than x. Let's pick the point C. At point C, it's equal to 0. And two, you need to show that at point C, it changes from being positive to negative or negative to positive. In other words, it changes concavity at that point. So the second derivative has to be equal to 0, and you need to show that it changes from positive to negative. So what does that look like with an actual example? So we've got x to the 4 minus 4x cubed. This was the graph that we just graphed the other day. Okay? We want to show that it has a point of inflection at x equals 2. So just to bring this one back from what we did yesterday, see if I can find it. Oh, I think I have it just on here. Let's pull that graph up. There's the graph that we did yesterday. Okay? They're saying that there's an inflection point at x equals 2. We're trying to show that point right there, that that's an inflection point. We've already graphed it. It does sort of look at that red point that the purple section is concave down, the green section is concave up after that. From just graphing it by hand, it naturally happened that way to be there. So now we're going to see how do we use our calculus to show that. Well, we would start things off the same way. We would probably be graphing this in total, so everything we did on yesterday's question we would do again. We're going to find our derivative for x cubed minus 12x squared. You know, if we had to find our maximum and minimum points, we would keep going with that and do all that work that we did yesterday. Now we just want to show that it has a point of inflection at x equals 2. So we find our second derivative, 12x squared minus 24x, sorry. 12x squared minus 24x. And so first of all, we need to show that we're going to have an inflection point if the second derivative is equal to 0. So we set our second derivative equal to 0. On this side, I'm going to factor out a common factor of 12x, leaving me with 12x times x minus 2, which means there's 2 points where the second derivative is equal to 0. And just like we did with the first derivative, we make a number line, and we label all of our critical points for our second derivative. And one thing I found that I really liked from watching an online video of someone doing the second derivative is, I didn't used to do this, but right beside here, I guess we're dealing with y. Just label it as y prime as a little reminder for yourself that to figure out things on this sign diagram, I have to plug things back into my second derivative. So I'm going to plug a value less than 0 back into my second derivative. And I like to use the factored ones. So if I plug in a negative number into my second derivative, can you see that 12 times a negative number is going to be negative? And a negative number minus 2 is going to be negative. And a negative times a negative is going to be positive, telling me this section is concave up. When I plug something between 0 and 2, like a positive 1, now 12x becomes positive. And 1 minus 2 is still a negative number. This section is negative, concave down. And finally, if I plug something in larger than 2, well, this is still going to be positive, but 3 minus 2, now this is a positive value. This section will be positive. So our statement, because this question said, show that it's a point of inflection. Our work, our math, has shown everything right now, but to write a statement to show that we understand what's happening, there is a point of inflection at x equals 2 since first thing that we need to show something's an inflection point, the second derivative at 2 equals 0. Okay? Technically, in this question, I should probably reword this. Okay? Because do we have f of x in our question at all? No. So by writing f prime of 2, I'm kind of making a mistake in my notation. 1. And this is why that function notation is so nice, because now I have to write it out in words. So the second derivative is equal to 0 at x equals 2. Boy, that function notation was so much nicer. I didn't have to write hardly any words. since y double prime, and you at x equals 2, yes. So you could, so if you wanted for this one, I would accept that. Y double prime equals 0. But it feels a little bit awkward because the function notation is just so much nicer. Okay, so first you have to show that, and then second, wow, the function changes concavity at x equals 2. And we could see that in the sign diagram. So now if we go back to our graph again that we had, we would have learnt from the first derivative the minimum and the stationary point of inflection. Those two black points we would have learnt. Then we would have learnt this red point from our inflection points. Our black point at 0, 0 would have come up again as an inflection point. When you go to draw it now, I like to start from my inflection points and draw from them. So just to pick a totally different color that we haven't used, that one, I would start from this inflection point and show concave up. I would go from this inflection point to this one, show concave down. And then from this one, show concave up for the rest of it. And by using your inflection points while you graph, you're going to get a really smooth curve that shows all of the things exactly. And one of the nice things about using your inflection points, especially at this one right here, by doing that, you're going to set something up that can show that there was a stationary point of inflection at that point. So basically, with inflection points, we've got all the tools we need to graph anything really, really well. All right, everybody done on this? So here's our first example. Sketch this one really, really well. That should be the instructions. Please sketch really, really well. Right? In pre-calculus, the question should have said, please sketch just okay. And now that we're in calculus, we can sketch really, really well. I don't know if that's, would be kind of confusing if that was the instructions. But find and classify all the stationary points. So we want to find all of our maxes and all of our minimums and all of our stationary points of inflection and all of our inflection points of this graph. So as our process, what we're going to do is start with our first derivative. Ooh, okay. Would we do anything preliminary? Yeah, there's going to be some preliminary stuff that we're going to do for sketching that's going to build on our grade 11 and 12 stuff. Can you easily find x-intercepts and y-intercepts? This one doesn't look like it would be easy to factor with the factor theorem and remainder theorem and all that. It would take some time. So we're going to say for our x-intercepts, it doesn't look like it would be easy to find. But can you see that you can easily find a y-intercept? You can plug in 0 for x. As a preliminary, a very good point to always include is your intercepts if you can. I can plug in 0 for x. It's quite easy to see that I'd get 0, 1. Okay? And although it doesn't come up in this one, I'm just going to make a note that there are no non-permissible values. Because for our critical points, we put where the first derivative is equal to 0, but we also put our non-permissible values. It's just good to note that there's no non-permissible values and get it into your habit of, okay, I'm going to see if I can find any intercepts and see if I can find any non-permissible values. With the non-permissible values, another thing that we're going to do for preliminaries is look for asymptotes. This graph has no asymptotes as well. So I was going to skip all the preliminaries because there really wasn't too much, because we skipped most of it. But just as us getting into a process, we're going to try and put all of our asymptotes, intercepts, right away, look at that before we get into the calculus parts. Now that I've done that, I go to my first derivative. My first derivative is equal to 3x squared minus 6x minus 9. I can set my first derivative equal to 0. This has a common factor of 3, which I'm going to take out. Did I make a mistake? Yes. What did I cancel out? Oh, this is the 3. Yes, thank you. That makes a lot more sense. X plus 1, x minus 3. And so we get that our first derivative is equal to 0 at x equals minus 1 and x equals 3. So we draw our number line, and we label minus 1 and 3 on our number line. Again, right beside this, I'm going to label f prime to remind myself when I'm plugging things into f here, I want to plug things into f prime. And I'm going to use my factored version here. 3 is always positive. But if I plug in something less than negative 1, this is negative and this is negative. Negative times positive. My original function is increasing on that interval. Between negative 1 and 3, if I plug in 0, this will be positive now. That one stays negative. I can already tell that at minus 1 I have a maximum. And if I plug in something larger than 3, all 3 of those will be positive. So now I can tell at 3 I have a minimum. So I can classify my stationary points. Stationary points. Okay? First one. Negative 1, comma. Now, to find the actual value of your stationary point, you're finding an actual value on your original graph. We always plug that value back into our original equation. So my original equation, if I have to scroll up here, 3x cubed minus 3x squared minus 9x plus 1. If I plug in negative 1 into that, I'd get negative 1 cubed minus 3 times negative 1 squared minus 9 times a negative 1 plus 1. Negative 1 minus 3 plus 9 plus 1. I get negative 1 comma 6. Okay? Classify it. Can you see that that is a local max? For the most part, if they don't ask for the reasoning behind it, I would say you've shown enough work here, because you set the derivative equal to 0 and you have your sign diagram. With those two things, it's obvious that that is a local max. If the question asked you to describe it, why is it a local max? You need to say 2 reasons. So I'm going to change color of pen here and just write the 2 reasons. Reason number 1 why it's a local max is because the derivative of negative 1 equals 0. And then reason number 2 is that the derivative is greater than 0 before x equals negative 1, and the derivative of x is less than 0 after x equals negative 1. And so I'm just basically describing the positive and the negative that we see on that sign diagram. Okay? I'm going to give you guys a group quiz on Thursday and Friday, and on that group quiz I'm going to get you to explain what why something's a max and a min every single time, just to practice. Okay? This, right here, this is called the first derivative test. That explanation is called the first derivative test. So 2, we have our second stationary point. Our second stationary point is going to be at 3 comma something. Again, if I want to find out what the y coordinate is, I'm going to have to go to my original equation and plug in 3. What do I get when I plug in 3? 3, 3, 3. I get 27 minus 27 minus 27 plus 1. 3 comma negative 26. Okay? Again, from our work, if they didn't ask us to explain anything, we can easily see that this is a local min. If we had to explain it, we'd have to say that same thing here, except now we'd say f prime of 3 is equal to 0, and we would say that f prime of x was less than 0 before x equals 3 and bigger than 0 after x equals 3. So step 1 of sketching will be doing your first derivative test and the sign diagram to find maximums and minimums. Next, we would look at our second derivative. Well, what's f double prime of x? Well, I look at my first derivative, which was 3x squared minus 6x minus 9. So my second derivative will be 6x minus 6. If I set my second derivative equal to 0, I can factor out a 6, and x is equal to 1. Draw my line, label second derivative, plot 1 on there, and we're going to see if it changes concavity. So again, beside that number line, I wrote f double prime to remind myself I have to plug things into my second derivative now. A number less than 1 would be 0. If I plug 0 into my second derivative, it's negative. If I plug a number larger than 1 into my second derivative, like 10, I get a positive value. So from here, we can say 1 comma something is an inflection point. Okay? How do we find out what that point is? Well, that point is on our original graph. So just like before, I'm going to scroll back up. I have to plug in. Wow, that's a big eraser. I wanted the little eraser. And then the medium eraser. Okay. Oh well. We would plug in positive 1 now into our original equation. So that means I plug in 1 here, and 1 here. It's going to be 1 minus 3 minus 9 plus 1. That gives me negative 10. So 1 comma negative 10 is an inflection point. Again, if they asked you to explain why it's an inflection point, the explanation needs 2 reasons. We would need to say that f double prime at 1 equals 0, and 2, at x equals 1, that the graph changes concavity. Before 1, the second derivative was concave up. After 1, the second derivative is concave down. So we need those two reasons. These are just the reasons. This doesn't have a name. Okay? In fact, I'm going to be, it has no name, but I'm going to specifically say, if we called the first one the first derivative test, it almost would seem, and most students get this confused, they would like to call this one the second derivative test. There is a second derivative test. This is not it. This is not the second derivative test. Doesn't it seem like it should be called the second derivative test? We do the same thing as the first derivative, but we use the second derivative, and it tells us something. It would make sense if someone had decided to call this the second derivative test, but no, they called something else the second derivative test. And there's questions that say, use the second derivative test to show, and lots of times students think of this as the second derivative test, and it's not the second derivative test. So I make a special note that this has no name. This is just the explanation, and it uses the second derivative, but it is not the second derivative test. Okay. So we used our first derivative test to find the max and the min. We used our second derivative, not second derivative test, just we used our second derivative to find our inflection point. We can now graph all the important points that we know so far. So what does that look like? Okay, here's our graph. The important points. What did I do first? Well, first in black, I found my y-intercept. So 0, 1, I'll label my y-intercept in black. Second, in blue, I found out -1, 6 and 3, -26 were maximums and minimums. So in blue, I'm going to label that point -1, 6, and then if that's 6, oh man, I should have done a different kind of scale, but I'm going to just estimate as best as I can. -3, -26 would be down there. Maybe I should have chosen my scale more wisely. Sometimes when I'm graphing, I start with the biggest value, the -26, and I plot that first, because then I can kind of scale everything else appropriately. Okay? I'm not going to take out a ruler and see if, you know, this should be 3.33 times greater a distance than that. And are you accurate to your ruler? No. If I give you graph paper, I assume that your scale is set up appropriately, but a little bit of estimation in there will be fine. And finally, after we found out our maxes and mins in blue, if we go back to our notes, we then went to green and found our inflection point at 1, -10. So if that's -26, +1, 1, -10 as an inflection point. So with that, we can draw our final graph. Okay? And like I said before, I like to start with my inflection point when drawing my final graph. I'm going to use a totally different color, purple, for my final graph. Here's my inflection point. I need to have everything to the left of my inflection point concave down. There's concave down. Everything to the right of my inflection point, concave up. And we've got our final graph, graphed very, very, very nice. It's accurate in that it has maximums and minimums. Okay? It's accurate in that it has its inflection point. The only thing that we could not find without our calculator on this one. So what would you have to use your calculator for? If you wanted to find your x-intercepts. In this case, you would need a graphing calculator because they ended up not being nice values. What I'm going to do is I'm going to show this on an entire page right now. Okay, and I'm going to get you to do the next one, following all the steps. The x one is an x to the 4 graph. We're going to find all of our stationary points, all of our points of inflection. Again, this one has no non-permissible values. Y-intercept is 0. I have the x-intercept I did at the end because I forgot, so if we want to look at it first, you could set your original function equal to 0 and factor it, and then you would get x equals plus or minus the square root of 2, as well as x equals 0 as x-intercepts. Okay. Now, first, start with our first derivative. Find our first derivative, factor it, set it equal to 0. Did you get critical points of 0, -1, and 1? Set up our number line and found out that your sign diagram went from decreasing to increasing to decreasing to increasing. Then our second derivative, which I have in the green there, I put right beside it, set it equal to 0. And you get x squared equals 1/3. Square rooting that, you get plus or minus the square root of 3. Set up our sign diagram there. And we see that it changes concave up, concave down, concave up. Now here I've got the points listed for both of them without the explanation. -1, -1 local min, 0, 0 local max, 1, -1 local min. And I plugged these values back into my equation. They actually weren't bad mental math. When you plug in negative square root of 1/3, well, it's going to get to the power of 4, which is going to get rid of this. It's like squaring twice. So you could get those values, all of these values so far, without a calculator. Not too bad. And then if we look at our graph, we can label our maxes and our mins. We can label our inflection points. I've done there in green. I labeled my x-intercepts in black. Something interesting from grade 12. If we look back at our x-intercepts, we have 3 of them, right? We have root 2, -√2, and 0. And in grade 12, can you see that the 0 one has a multiplicity of 2? Remember, when something had an even multiplicity, it bounced off the x-intercept. So we can see in our graph, that's exactly what's happening at x equals 0. And the other ones happen only once, so at those x-intercepts, your graph just goes straight through that point. So a little review from grade 12 pre-calculus. For some of you last semester, for some of you last year.